Hello and welcome. This is another open process problem. We have a completely evacuated cylinder whose volume is given to us, and the valve is open and outside air at 100 degrees Celsius, 100 kPa, 30 degrees Celsius enters into the cylinder. We are asked to find the final temperature and the entropy generated during the filling process. Our first thought will be if outside temperature is 30 degrees Celsius, nothing happens here, the air enters here, so the final temperature should be 32. Well, not quite, because when the air enters, a considerable amount of flow work is done. Outside air is pushing the air in. So all this energy that enters the cylinder in the form of work, flow work, has to be stored somehow, and that raises the temperature we'll find. Okay, let's use the TESTapp to verify that. So obviously we are going to follow the open system unsteady process branch, and in this problem we are asked to use the ideal gas model. So we click the ideal gas model and finally go to the HTML tab to launch the app. Air is the default fluid already, so state 1 will be our beginning state, complete vacuum. Just because we will do a parametric study with volume, let's define volume here. Let's call it, say, VOL equals 1 meter cube, so that later on we can change it. So if I do a calculate here, it registered my change, volume equals 1 meter cube. SI unit is the unit for IO panel. So now, for state 1, instead of volume being 1, we can write equals VOL. If I do a calculate, you can see its number is picked up, which will be shown. Always remember, when you move the pointer over a variable, its information appears there. So you can see the volume equals 1 meter cube. Okay, how do you create vacuum in this? Of course, vacuum means there is no mass. That's the first thing. And then you can either put pressure 0 or temperature 0. I like pressure 0 because it's kind of more intuitive. There is no molecules, no pressure. And that defines vacuum. As you can see, the picture here is completely dark, kind of depicting vacuum. Okay, so even though it's vacuum, it's a finite volume, remember that. Now for state 2, we only know the final pressure, because at the end of the filling process, the pressure will be same as atmospheric. Pressure will equilibrate very quickly. And of course, the volume must be same as volume 1, or we can just write volume, VOL in this case. So of course, that's not enough information to find state 2. State 3 is the air that is getting in. That's the outside atmospheric air. So it's at 100 kPa and 30 degrees Celsius. That's given to us. But of course, we don't know how much air entered. That's one of the things we want to find. So with that, let's go to the process panel and set up the process. We can see it looks complicated, but really we have on the left side, we have a B state, which we begin with. State 1 is our B state, air at state 1, complete vacuum. And final state is, which is totally not completely known, is state 2. And we have a filling process, so only the inlet should be populated, and there is no exit. It's left at, the exit is left blocked. And also it's given the cylinder is insulated, so there is no heat transfer. And of course the cylinder doesn't expand or contract, so there is no boundary work. So with that information, if I now do a calculate, it should solve the energy equation. And in the energy equation, we know there is no heat transfer, there is no work transfer, and there is no exit at all, only inlet state, which we know the J for. And obviously there is no mass in the beginning, so the energy equation reduces to EF equals Ji. So anyway, so it is because Ji is known, now the state 3 E can be substituted. Let's go and take a look at the state panel. As you can see, if you go to state 2, yes, E has been substituted. So a calculate here will produce the final temperature. As you can see, the final temperature is way higher than the temperature at which the flow went in, which was 30 degrees Celsius. So it's now 149 degrees Celsius. How about the entropy generation? Come back to the process panel and you can see how much entropy has been generated as a result here. Now, will the volume of the cylinder have any impact on this phenomenon? Let's go find out. So 149 degree, let's write it down somewhere, is our final temperature. How do you do the parametric study? In the IO panel, we just go and change the volume, say to twice the volume, and calculate here to change the volume. Do a super calculate. It will not only update all calculations, it will also produce a report and test codes. Go back to state panel. Yes, the temperature hasn't changed at all. So the final temperature doesn't matter what is the volume of the tank. You can do similar parametric studies very easily.